Hello IGCSEs, hello, I'm Lara, this is Theatre of Science. I am trained to teach physics at level, and this is the bit of my job where I actually get to do that. So I stream free live all ages lessons for home educators. If you're watching live, we're doing woodlands at the moment. They can be on any topic. I stream Lego stories, but yeah, this is where I really get to dig down into the subject that I trained to teach. So thank you for being here with me. I will tell you at the end how you can support these lessons. If you are thinking this is weird, how she just teaches for free. I kind of don't actually. Most people watching are paying me, but there's no obligation. We'll talk about it at the end. Right, shall we talk about sound? What a lovely topic for a lesson. We've got some great activities. We'll rewind a little bit because I made an apology last lesson and I sort of have to make the same apology this lesson, but for different reasons. So we have learned throughout the course of this course about two different kinds of wave, and they both involve vibrations. If you're new, don't worry, there's no pressure on you. If you're not new, you should be able to name those two types of wave by now. Here's the first one we talked about, the transverse wave. The definition of a transverse wave is a wave where the vibrations, so in this case like it's vibrating up and down, are at right angles to the direction of energy transfer. So imagine a slinky on the ground, you vibrate it that way, like side to side, the energy would travel at right angles to that, okay? And the other kind of wave, this is the one that we've talked about most, like light, microwaves, radio waves, waves on the ocean, they're all transverse waves. There's another kind of wave, which we've mentioned a bit, which is like pinging a slinky, where the vibrations are in the same plane, they're parallel to the direction that energy is transferred, all right? And we were sort of, don't say this in your exam, but you know, if you ping a slinky from side to side, the energy also sort of gets transferred from side to side, all right? So, longitudinal waves are the waves that we're talking about today. And the first thing you need to know for your exam is that longitudinal waves have areas of compression. So I think you're just going to be able to do this, because I think you've probably come across the word compress in human lives. Can you just give an area of compression a piercing stare for 5 seconds, please? Are you doing it? You've got a diagram of a longitudinal wave on the board. There's bits where the slinky is squished up. Which the areas that are compressed. Yes, well done, exactly. So I shouldn't be saying squished because this is GCSE physics. I should be saying areas of high density, but we haven't done density yet. But basically it just means the particles are close together, okay? All right, there's another thing about longitudinal waves you need to know, and it's a word that you don't often come across in everyday life. It's called rarefaction, but I think you might be able to work it out given what we've just done. So here's another wave for you. This is lots of particles vibrating to and fro. This is a longitudinal wave, and particles are close together, squished, densely populated areas. And some of the areas, the particles are more spread out. Which bits of that wave do you think are areas of rarefaction? Give it a piercing stare. Go on, you really pierced that area of rarefaction. Have you guessed? Have you got an idea? Yes, it's the bits that are not areas of compression. That's right. So the only tricky bit there, I think, is remembering the word rarefaction, which is not a word that you come across, really. We would say areas of low density, okay? To make things joyfully confusing today, we are going to be drawing sound waves like this. We're going to be drawing them as if they're transverse waves, because it's just going to be easier to picture. It's easier for our purposes, but a better model would be drawing them like this. So what actually are sound waves? Well, glad you asked, friends. Can you get a piece of string and tie it to a spoon like this? I know a lot of you have done this with me already, but there are no apologies here. This is a great activity. So you literally just get a piece of string and tie it in a knot around the head of a spoon so that the spoon hangs from the piece of string like this, okay? There you go. Right. So yeah, how we traditionally draw longitudinal waves to kind of show that they're longitudinal, do this. Just lines on a board, basically. If you wanted to show the areas of compression and rarefaction, you might do that. But a lot of the time today, we're just going to be drawing them as transverse waves. Okay, so if you've done that, well, while you're doing that, actually, let's have a look at the starter question that was waiting for you on the board as I faffed around. Before the lesson began, I asked you, which of these is essential for a sound to be made? Echo chamber, waves, vibrations, air, particles. I mean, I'm not testing it because, like, you might not know. That's kind of the point of the lesson, is me telling you. You might be able to guess now if you didn't know before. They need particles to travel. Sound waves absolutely need particles to travel. That's what they are. And they also require vibrations. Yes, they don't need waves. I mean, sound is a wave, so that answer just didn't really make sense. Once sound is happening, you've got a wave. It doesn't need that the sound travels through. We'll come to that later. Can you please... Well, one of the things that you need to know is that a medium is needed to transmit sound waves. And a medium, it's like a posh way of saying stuff, really. Glass, air, water, wood. These are all different mediums, things made of particles. If you've got your spoon now hanging from a string, can you just whack it against something, like the wall or a chair? Make it make a nice tingy noise, yeah? So what's actually happening? And I'm saying it like, oh, you know, this is obvious, this is just basic physics. What's actually happening is that you're making the spoon vibrate. So you're making the spoon oscillate, is a good physics word for it, kind of move to and fro. And that is making the air particles around it vibrate, move to and fro. And those air particles are knocking into air particles, which are knocking into air particles, which are knocking into air particles. And eventually, some of those air particles knock into your eardrum. So your eardrum vibrates, oscillates, and your brain translates those vibrations as sound, which is ridiculous, isn't it? Like, this isn't even the activity. This isn't the interesting bit. And that's wild. Like, what? The human brain. Anyway, so that's why sound needs particles to travel, because sound waves sort of are particles. Sound is a pressure wave. So you could imagine the air particles behaving just how they looked in that diagram. Areas of compression and areas of rarefaction, where the particles are, the air particles are more dense or more spread out. And that's not just with air. Any kind of medium can act that way and create this kind of pressure wave. That's what happens when earthquakes occur, isn't it? There's waves travel through the ground. Anyway, I'm getting ahead of myself. So yeah, you might already know that because you might have come across the film Alien, which has the most magnificent tagline. It's just been helping people pass IGCSE physics for years, probably. The tagline for Alien is, "In space, no one can hear you scream." It's a brilliant tagline. It's really scary, but it's also, yeah, scientifically accurate. No one can hear you scream in space because space is a vacuum where there are no particles, so sound waves cannot travel where there are no particles. So this is the first thing you need to know for your exam, is that a medium is needed to transmit sound waves. Right. I'm going to give you this to do, and then we'll do the next part of the activity. Okay, just a quick sort of question sheet for you here. I've got 6 facts about light waves. All of these 6 things are definitely true about light. Can travel through space. Light travels slower through glass than air. Okay, we've talked about that before. Light hits glass, it slows down. Light waves can be reflected. Light waves exist that can't be detected by humans. That is true. You can kind of call radio waves and microwaves and infrared light waves, just light waves we can't see. Light waves can be refracted. We talked about that last week. And light waves are not pressure waves. So if just for each of those, can you say the same thing about sound waves? So write yes or no, or put a little bit of an explanation if you like, next to each case, please. Some of them you should know from previous lessons, and some of them hopefully you just learned them from me. So I'm pausing there because I'm looking around for my jug of water and realising I've left it downstairs. Won't be long. Have you done? Should we move on? I want to get to this activity. This is going to segue us beautifully into the activity that we're doing. Okay, so light can travel through space. Obviously, that's how light gets from the sun to us. Sound can't travel through space because sound is a vacuum. Space is vacuum where there are no particles. We just said that. Hopefully, you got that. Light slows down when it hits glass. That is actually not true of sound. We'll go into that in a sec. Light can be reflected, and so can sound. I told you that very briefly because I started last week's lesson by holding up a piece of paper that I had in my hand not seconds ago. And that piece of paper said, it said that all waves can be reflected, refracted, and diffracted. And sound is a wave, so yes, sound can be reflected and refracted and diffracted. There are sound waves that exist that can't be detected by humans. We'll talk about ultrasound next week. Yes, sound is a wave, and all waves can be diffracted. Light is not a pressure wave, but sound waves are pressure waves. Right, let's concentrate on this bit, shall we? Because that's the bit that I thought you might be a bit confused about. Because we've talked a lot about how light slows down when it hits different medium, and I've sort of keep saying, oh, it's a bit like us, you know. Imagine that you were walking through some air and then you hit some water and then you hit some treacle. You can kind of imagine that the kind of denser the material, the more you would slow down, and the same thing happens to light. But sound, it's not the same. So we'll actually look at this after the summer holidays. We will talk about this in more detail. It's a bit of a spoiler really, but I don't know if you know that the particles in a solid are very close together. The particles in a liquid they're still touching each other, but they're not quite as rigid. They're more loosey-goosey. And the particles in a gas aren't touching each other at all. So the particles, that's why you can do this through air, because particles of air are not bonded together. Right, can you get your spoon and your string? What you've got to do, be careful, because hearing is so delicate. Can you put the bits of string in your ears and then whack the spoon against the wall again and see if you experience anything different to what you experienced the first time we did that? Okay, so we were just hitting against the wall, hearing quite a nice sound. Now can you put the string in your ears and do it again? It's not very good telly, because you can't hear what I'm hearing. Oh, it's so good! It's so good! I taught this lesson into the internet 2 years ago, and I watched it the other day, and I say at the time, I feel so sorry for people who have string and spoons in their house and they don't know that they can do that. It's amazing! So why is that happening? How and why is that happening? Well, it comes down to this. It's about how particles in solids and liquids and gases behave. I won't do it again. Hopefully you're doing it at home and enjoying it. Yeah, so light is like us. Light can travel easily. It can travel most easily through a vacuum where there aren't even any particles to slow it down. I suppose we can't do that because we wouldn't be able to breathe. But we travel more easily through gases than we do through liquids, and we definitely don't travel very well through solids. But sound, what is sound? Sound is particles vibrating into each other, isn't it? Like dominoes. It's actually quite hard for sound waves to travel through air. I suppose I should say it's like hard for air to form sound waves because the particles have got sort of quite a long way to travel. It's not going to carry the sound as efficiently. It's easier for sound to travel through water because water particles are bonded to each other. But it's much easier for sound to travel through solids. So sound travels, I think, 10 times faster through wood than it does through air because the particles are right next to each other. They're all set up for bashing into each other, aren't they? I mean, you could, if you wanted to, I'm not going to, but if you put your ear onto like a wooden table now and then you knock the table, you'll find that the sound gets carried to your ear very easily. Now, you might be able to think of a scenario. You might be able to think of something that happens in real life and be thinking, Lara, my experience of the world is telling me that what you're saying is nonsense. You must be wrong. It can't be true. Can you think of what that is? It's like a sort of a fairly common scenario, I suppose. I'll draw this swimming pool for you. Drawing it, yeah? Visualising, helping your understanding. You might have noticed that if you're at a swimming pool and there's lots of noise all around you, I don't know, this person's singing. If you go under the water, you would think, well, what you've just told me is that sound travels more easily, sound travels faster through liquids. So you would think that the sound doesn't travel very well maybe through the air, but once it hits the water, it travels to me really easily and I can hear more clearly. And that's not what happens, is it? If you've ever dived down to the bottom of a swimming pool, or just stuck your head under the water, do it if you're in the bath as well. All the noise above you suddenly gets all muffled. That's because the sound is having to travel across a boundary, and it doesn't like doing that. If you, next time you're at a swimming pool, or indeed in the bath, if you tap the side of the swimming pool while your head is in the air, and then you go down and duck your head under the swimming pool and you do the same thing, tapping the side in the water, you should find that you hear the sound much more clearly in the water. Do it in the bath. You don't have to go to the swimming pool, do you? But yeah, it's because sound does travel faster through solids and a bit faster through liquids. But yeah, it doesn't like crossing the boundary. Right, okay, moving on. Oh yeah, so some of this is just a memory game, right? There's something here that you just have to remember it. We're not going to bang on about it because you're just going to have to revise it like a couple of days before you do an IGCSE physics exam if you end up doing one. So you have to know that sound travels faster in solids than in liquids, and faster in liquids than in gases. So it travels most slowly through gases and fastest through solids. I don't think you should remember that. I think you should understand that. That should be something that even now, hopefully, has more or less made sense in your brain. That's not a memory game. But this one, that's just numbers, isn't it? The speed of sound in air is approximately 330 to 350 meters per second. If you're not working with that number all the time, I don't know how you're going to remember that. You're just going to have to remember it. Maybe you just love physics and you're reading so much about it. All right, let's quickly talk and then do a little about how changes in amplitude and frequency affect the loudness and the pitch of sound waves. Whew. Right, first, there's a lot of words in there, aren't there? First of all, I think we need to remind ourselves of what frequency and amplitude are. And you might not know what pitch is either. You have seen this question before. Do you know what the frequency of that wave is? Can you remember what frequency is measured in? I guess frequency is a word we use, isn't it, in everyday life? How frequent is something? Yeah, that makes sense. If I said to you, how frequently does your neighbour cut their grass? Or how frequently does... I'm trying to think of an example. How frequently do you blow your nose when it's the summertime? Frequency is how many waves pass a point per second. Okay, so you also have to know what a wavelength is. Oh, we've talked about this before, so I'm hoping that people who've been before remember. Basically, the wavelength of a wave, you can measure it from any point on the wave. You just trace the wave until you stop repeating yourself. So the easiest way probably is to say it's from peak to peak. So from there to there is one wavelength. From there to there is one wavelength. But from there to there is one wavelength as well. So here, half, if this is on the x-axis, this is time, we can see that half a wavelength has gone by in 1 second. So you would say that the frequency of this wave is half a wave per second. So it's 0.5 hertz, because hertz just means per second. That was a lot. If I would expect you to kind of know that already at this stage, really. So if you're new, sorry, don't expect it to always be this confusing. So what frequency does is it dictates something called pitch. The easier it is for a thing to vibrate, the higher the frequency of the wave. Quite confusing. Let's do another activity. The easier it is for a thing to vibrate, the higher the frequency of the wave. You might know this from everyday experience. I think I said to bring a big elastic band with you, did I? If you get an elastic band and you twang it, you will sort of see how many waves appear per second. So what pitch is? Pitch is how high or low the note is. So again, I'm drawing it as a transverse wave, but if you imagine that's a standard wave, if we increase the wavelength of that wave, if we decrease the frequency, less waves per second, that is a low note, the pitch of that note is very low. And if we increase the frequency, more waves per second means the pitch is very high, okay? It's easy to remember now, it's harder to remember once we start throwing volume into the mix. But yeah, the frequency of a wave, that's what dictates how high the note is. And the easier it is for a thing to vibrate, the higher the frequency. I guess that makes sense. Let's do this activity with a wine glass because it's a cool activity. So what I want you to do is to just put a little drop of water, like a couple of centimetres, not too much water, into, it's best with a wine glass. You can get it to work with any glass. And then wet what we have started calling in theatre science your front knuckles. Sounds rude. I don't see how it is. The bit of your hand, the palm of your hand that's on the other side from your knuckles. I think this is the best way to do it. And what you do is you just put your front knuckles, it really does sound rude, on the top of the wine glass and just move around in a circle and see what happens. Straight away, I am using my best wine glass for the job though. Whoa, isn't that so lovely? If you're doing this with me, you can probably actually feel the vibrations. And you might well be able to see the vibrations in the water of the glass. Now, this lesson is about sound. So I don't really have time to talk about the physics of why this is happening. Very basically, you are pulling the particles of the glass and then letting them go again, so they are vibrating, right? We've got the two ingredients that we need for a sound wave to happen. We've got vibrations, because you're vibrating the particles of glass, and we've got particles of glass and particles of air that are transferring the wave to our ears. And it's basically, if you know how, like, if you push a swing, you just instinctively push the swing to make it swing more. You don't push it in a way that makes it stop. You're doing that with the glass particles. You're pushing them so that they vibrate more. Beautiful. Right. The easier it is for a thing to vibrate, the higher the frequency of the wave. So, if we add some more water to this glass, are we going to hear a lower frequency wave? Are we going to hear a higher frequency wave? What do you think? Let's try. The easier it is for something to vibrate, the higher the pitch of the note, the higher the frequency. I should have made a note of what note was playing before, but hopefully we can remember. Okay, so I'm going to do the same activity again, but I've put more water in my glass. What do you think? Is it going to be a high note or a low note? Oh, it's much lower, right? Let's double check. Wow, you can really clearly see the vibrations there. It's much lower, right? We've added more water, which has made it harder for the glass to vibrate, so the note has got lower. Or I should say, I suppose, the frequency has got lower, or the wavelength has got longer. Okay, so another, very much for me, just a memory game before I give you a little quiz about that. You have to know for your exam that the frequency range for human hearing is 20 to 20,000 hertz. I should have said 20 hertz to 20,000 hertz, okay? You have to know the frequency range for human hearing. So humans can hear a sound wave which is travelling at 20 hertz, 20 times per second, 20 waves per second if you like, passing a point. And we can hear waves where 20,000 waves are passing a point per second. We can't hear lower and we can't hear higher. This changes. If you're younger, you can probably hear a wider range of sounds. As you get older, well, you just start to fail, don't you? And you probably won't be able to hear quite as low or quite as high sounds. How are you going to remember this? I don't know. I've got a past GCSE question on it quite soon, which is designed to trick you. So let's see if it does. 20 hertz. You can hear. So 20 hertz you can hear, 21 hertz you can hear, 100 hertz you can hear, 500, 5,000. Once you get higher than 20,000 hertz, you can't hear that sound anymore. Okay? Great. Right, a very quick note on volume before I give you this quiz. Do you remember what the amplitude of a wave is? You remember they're going to test you on that. They're going to try and trick you. Everyone thinks the amplitude of a wave is from the top to the bottom, from the peak to the trough. It's not. It's how far the wave gets from the midpoint. So that is the amplitude of the wave. And the bigger it is, the louder the sound. Yeah? I mean, that makes sense, doesn't it? The taller wave, the louder it is. Let's see how you get on with this. So I'm going to make a sound, and what I've got is basically 4 pictures of sound waves. I'm going to make a sound, and I want you to tell me here, A or is it B? Okay, so there's a picture of, here we've got a picture of, let's just call it a standard sound wave. It's two waves there. So let's say that's a frequency of 2 hertz. A is and B is 2 waves, but it's got a smaller amplitude. Okay, here's your first sound. That's your first sound. And here's your second sound. First sound, and the second sound. And the first sound. And here's the second sound. Everybody now, the first sound. And the second sound. You worked out if it's A or B that I'm showing you there? First sound, second sound. Well, what's happened? The note has got lower, right? The second sound is lower. The pitch, like how high or low a note is decided by its frequency, and it's lower, so we're looking for fewer waves per second. So it's this one, right? If this is 2 waves per second here, this is only 1 wave per second, so it was A. All right, let's do the second one. You ready? So this is the first sound, and this is the second sound. Here's the first sound. Here's the second sound. Everybody now, first sound. And the second sound. First sound. Second sound. Have you got it? It's B, isn't it? So the first sound, again, is 2 hertz, you could say. We'll just imagine the x-axis here. That's 2 waves per second. This one's also 2 waves per second, so it's the same note. It's vibrating the same amount of times. It's the same pitch. But this one, the amplitude is much bigger because it's louder. Okay. All right, number 3. Here's the first sound. Here's the second sound. Here's the first sound. Here's the second sound. If you're a good musician, here's the first sound. I've not paid any attention. What's the second? How much these notes are actually vibrating, my apologies. This is not, the ratios are incorrect. First sound. Second sound. First sound. Second sound. Did you get it? It's A. That's a higher frequency, more waves per second, so a higher pitch, so a higher note. So it was A. Okay, trickiest one. Number 4. First sound. Wait, I'll make it a different note. First sound. And here's the second sound. Gotta listen carefully. First sound. Second sound. And the first sound. And the second sound. And the first sound. And here's the second sound. Clap your hands now. Have you got it? Have you got what I was trying to do? Yeah? So, did you spot that? Have you got it? I don't want to interrupt you if you're thinking, if your brain is working hard. I don't want to spoil it by telling you. Have you? So the second, number 4, all these images show the same wave. I've made the wave in B slightly greyed out because I want to trick you and think maybe you would think that meant that one was quieter. It's not quieter. That's not what I just told you. The greyness of a sound wave doesn't decide anything. So that's exactly the same as the first sound. And A is also the same, except I've just flipped it upside down. But that doesn't matter, does it? Because we're talking about the frequency. And here, if this is 1 second, this box, that's 2 waves per second. And this one's also 2 waves per second. It's just flipped. Right. Here is a sketch of a sound wave, just to make sure you've understood this. And I must admit, I tried to do it alongside everyone yesterday, and it's harder than I thought. Here you've got a sketch of a sound. It's the one that I just showed you. It's 2 wavelengths long, so we'll say that this box is 1 second, so this is a frequency of 2 hertz. If you've cut from my website, you've got 2 little boxes, or you could just do this on a piece of paper. Can you please sketch a sound that is identical to this sound, but louder? And can you also sketch a sound that is identical to that sound, but higher? I'm going to do it again because, like I say, neat PowerPoint for you, but when I actually tried to do it with my hands, I found this quite difficult. Have you done it? I have done it, but then of course I did it yesterday as well, so I've got a head start on you. All right, I'll show you mine. Now, if this is the standard wave, yeah, I made a very foolish mistake yesterday on Facebook because that's the standard wave, and I thought, okay, to get it louder, it needs to be exactly the same but higher. But to make it exactly the same, I started drawing it from the same place, and obviously you can't do that because it's a taller wave, so you've got to start from higher up. I left it like this on purpose because this is a very bad sketch, isn't it? This is really very bad indeed. It's way more on one side than it is on the other side. But I think you'd probably still get marks for that. Oh wait, no, you definitely wouldn't. Oh no, you wouldn't. Wow, this is why it's really good for me to do it alongside you. Look what I've done wrong. So I've made it bigger, but I've accidentally only made it one wavelength, hasn't it? I've reduced the pitch. I've made it a lower frequency, so that's 2 waves per second. That's only 1 wave per second. So that wouldn't be answering the question. I've made it louder, but I've also made it a lower note. So I would possibly get like 1 mark out of 2 if that was an exam. I should have done that. There we go. Yeah. So I don't think it really matters how neat it is, and I'm sure they would give you squared paper or something. They wouldn't make you freestyle like I did. That's the right answer. And then the higher note, I find that a bit easier. It's just the same as the first one, but you've got to fit more waves in. Got to be a higher frequency. Okay, right. Are you ready for some IGCSE physics questions? Yeah? Are you? Okay, so I've got 4 questions which are designed to be the kinds of questions that you would get at IGCSE. This first one is an absolute cracker. You ready? Here we go. And then we'll call it a day. So, you've got a table here. You've got K, which is slightly towards the right of the table. It's not in the middle of the table, it's to the right. A hand knocks on the table at K, okay? So you've got knocking on the table towards the right-hand side of the table. You've got a microphone above, which is microphone number 1, floating there above K. You've got microphone number 3, which is just below the table, so the same distance away as microphone 1, but below, not above. You've got microphone number 2, which is at the edge of the table closest to K. It's a couple of centimetres away from the table, hovering in the air. And you've got microphone number 4, which is on the far left of the table, and that is actually touching the table. Which of those microphones will pick up the sound first? Isn't that a great question? So good. What do you think? Which of those microphones will pick up the sound first? This is really tough. I mean, if you're thinking, well, it's quite easy, then maybe that's because you just did a lesson on sound. But I think if you got this kind of out of the blue in 2 years' time, this is a cool, challenging question. Have you got the answer? So you have to remember, it's not really about how close the microphone is to K. Do you remember what I said? Boundaries. Sound waves do not like crossing boundaries. So microphone number 2 is closer to K, but the sound wave has got to travel from the wood and then across this gap. And sound doesn't like to do that. Sound waves travel 10 times faster through wood than they do through air. So it's microphone 4 that will pick it up. Just like your ear if you put your ear on the table. That's a great question, I think. Right, next one. You've got sound wave here. It starts off small and it gets bigger. But which sentence is correct? The sound is getting louder. The sound is getting higher. The sound is getting louder. The amplitude of the wave is decreasing. The wave is decreasing. So you've got a sound wave. I'm just going to say like it starts small and then it grows bigger. But is it that A, the sound is getting higher, B, the sound is getting louder, C, the amplitude of the wave is decreasing, or D, the frequency of the wave is decreasing? Which one of those is true? Only one of them is true. The answer is, well, it's not about pitch, is it? It's not about high or low. That would be the frequency, like the amount of waves per second. It's getting louder because its amplitude is increasing. Number 3. Which of these sound waves could not be heard by a human? Which of these sound waves could not be heard by a human? Is it A, a frequency of 2, little k means killer, okay, like a kilogram. So is it 2 kilohertz, 20 kilohertz, 200 hertz, or 200,000 hertz? Which one of those frequencies could not be heard by a human? Again, brilliant question. Which of the sound waves could not be heard by a human? Oh, what frequency can humans hear? Can you remember? So yeah, the little k means like 1,000, in the same way that you get 1 gram and a kilogram is 1,000 grams. A kilohertz is 1,000 hertz. So 2 kilohertz, 20 kilohertz, 200 hertz, and 200,000 hertz. Have you got it? So humans can hear between 20 hertz and 20,000 hertz. So 2 kilohertz is 2,000 hertz. 2,000 is between 20 and 20,000, so yes, we can hear A. 20 kilohertz is the very top range that humans can possibly hear. Yeah, we can hear between 20 hertz and 20,000 hertz. 200 hertz, yep, that's still within 20 and 20,000, isn't it? So it was D, it's the last one. 200,000 hertz is too many zeros. We can't hear a frequency that high. Finally, this one's quite tough, actually, I think. You sort of think it'd be easy. How could they possibly make a question like this difficult? But I think they have. A person pulls on a slinky and produces a wave as shown. Could you please label an area of compression and an area of rarefaction? A person pulls on a slinky and produces this wave that you see here. There's some parts of the slinky are squished together and some are spread out. And they've sort of put lines across the slinky to split it up into bits. Can you label an area of compression and an area of rarefaction? I think they've done a good job of making a simple thing quite difficult. Because you might have thought, well, like, oh, that's obviously an area of compression where it's close together, and areas of rarefaction always next to areas of compression, and they've drawn these confusing lines, so you might have thought that wasn't... No, just trust your instincts. Compression is the bits of the slinky that are close together, so just circle the bits that are closest, and the areas of rarefaction are the bits where the slinky is furthest apart, to be safe. So, yeah, any of those bits, okay? The bits where the slinky is far apart. Woof! Right, you lot, that is the end of our IGCSE physics lesson about sound. Thank you so much for joining me. I really enjoy teaching IGCSE physics, and I really enjoy the fact that you come and like these videos and subscribe. I also like the fact that sometimes you comment. YouTube seems to have, it went through a phase of allowing people to comment on videos for children, but I keep setting them up that you can comment, and it keeps not allowing comments. So I think it's probably changed its mind again. But I always say that when I'm live on YouTube, there's no comments section, but I've always put a post up on Facebook saying that you can comment on that post, and I'll go to it and say hi at the end. So I'm going over to my Facebook page now. I can see some comments. I'm going over to my Facebook page to see if anyone has left me any comments. So if you're on Facebook, if you're not, good for you, frankly, but if you are on Facebook, then feel free to pop over right now and I will say hello. Hello, Jacob. Is that Bastian as well? Hey, hello Jacob and Bastian and Hannah, who is baking and doing this at the same time. Amazing. Oh, and there's Freya and Edmund. Edmund is looking forward to today's lesson. He's been watching YouTube videos of music played on a glass harp. Oh, yeah! Which is lots of wine glasses with different amounts of water in. Sounds really amazing. Yes! Big fan of the glass harp. Also, hello Willow and Darcy and Jackson. All right. And there's Freya again. Oh, nice. Thanks, you lot. I'll just have a little refresh in case anyone didn't know that you could do that and is now doing that. If you want to support me, I mean, I think most of you are. Like, most of you, if you're in lesson, like, 8 of IGCSE physics, you've probably heard me say this before. But just in case you haven't, how this works is, I am trained to teach physics to A-level. I had to get a physics degree, and then I had to train to teach physics. And then I got teaching experience in a school. And then lockdown happened, and I started streaming lessons online. And the home educating community liked that. So I wanted to keep doing it, and you wanted me to keep doing it. So I set up a Coffee page. There's this website called Coffee, where you can just send people money. And you are now sending me money, and it's amazing. It's so cool that I don't even have to like keep anything behind a paywall. So all of the printouts, my mantra for my business is, I'm not going to hold anything back from you that would help you to pass an exam. So printouts help make the lesson more accessible, so they're all free. The lessons are free. It's all saved on my website for watching. I'll catch up for free. But there are some nice things that I will send you if you sign up on Coffee, just to kind of, you know, like motivate you to sign up, because if you don't sign up, I don't get any money, and then I can't do this for a job. I send you some diffraction glasses. Yeah, you're GCSE physicists, so we're going to call them diffraction glasses now. They make you see rainbows. They're amazing. They diffract white light. They make it spread out. I'll send you a description of how that works as well. And I will also send you Theatre of Science magazine. Oh man, I worked so hard on this. It's the magazine that I want to read, like, as an adult. It's got just the right amount of detail for me. So if you sign up with £5 a month, you get the mould one. It comes with a free home compostable plastic bag so that you can grow some mould and identify it. It's got a comic about how penicillin was discovered. It's got loads of information about mould and fungus. It's got a choose your own adventure. And if you sign up with £6 a month, I'll send you that one and the sleep issue as well. Although I'm running out of sleep issues. So if you really want a sleep issue, you should sign up now. It comes with a little bag of organic lavender and some fabric. You can sew a little sleep squish. Again, it's got a choose your own adventure. It's got a jigsaw, this one. That was a good idea. It's got a beautiful comic about sleep. It's got an origami koala, because koalas sleep the most of any animal. So yeah, and then you'll be on the list to receive Theatre of Science magazine once I've managed to get it written. Right. I think that is everyone. Yeah, we've had everybody's comments. So I am going to go and get a honey and lemon. I've said hello to everyone. Yeah, Bastian's here, Mika of the paper that I've been showing everybody in today's paper making lesson. Thank you so much. Hannah, I hope that what you're baking works out extremely well. I might go do some baking myself. Yeah, just do some not looking at a screen for a bit. And I will see you all next week. We've only got, is it 4 lessons left, I think? 4 lessons left until the summer holidays, and 4 lessons left on sound. And then that'll wrap up our first year of study. And then we've only got 1 more year. I say only. We'll be halfway through, which is quite exciting, if you are planning on doing an IGCSE physics course. So yes, I'll see you next week for another sound lesson. Bye. Thank you for joining me.